Lecture 4, Addition and Vector Spaces. In the last lecture, we saw that the definition of free abelian group, while looking complicated, was actually fairly simple. We just counted objects which we might have labeled with symbols such as x1 through xk, or we could be counting roses and coneflowers. In either case, we just have a linear combination of our objects where we do addition by combining like terms. We will now define free vector space. Note that the only difference between a free vector space and free abelian group is that our coefficients need not be integers. So, for example, if we work over the real numbers, our coefficients could be pi, square root of 2, or 3. Or we could use rational numbers, i.e. fractions, and our coefficients could be, for example, 1/2 and 4. We will mostly work in Z mod 2, where our coefficients can only be 0 or 1. We don't actually need to know the formal definition of a field, since we will stick with using Z mod 2 coefficients for the most part. But for completeness, I will quickly summarize a few definitions. If G is a group under an operation such as addition, then G needs to be closed under addition. So if I take two elements in G, their sum is also in G. For example, if I add two real numbers, I get a real number. If I add two fractions, I get a fraction. If I add two whole numbers, I get a whole number. And if I add two elements in Z mod 2, I also get an element in Z mod 2. So all of these sets are closed under addition. For the last one, let's go ahead and check that out quickly. If I add 0 plus 0, I get 0. 0 plus 1 equals to 1, which is also 1 plus 0. And the last possibility is I could do 1 plus 1, but that equals to 0 mod 2. So in each case, when I take two elements in Z mod 2, if I add them together, I get either 0 or 1. So Z mod 2 is closed under addition. To be a group, I also need the associative property. I also need an additive identity. So there exists an element, which we will denote by 0 in G, such that when I add it to any other element in G, I get back that same element. So 0 plus x is the same thing as x is the same thing as x plus 0. We also need inverses. So that means if x is in G, then we also have its additive inverse denoted by minus x. That also needs to be in G, such that when I add together x and its additive inverse, I get 0. If G is an abelian group, then I can also commute elements before adding them. Examples of abelian groups include the real numbers, the rational numbers, the set of integers, as well as Z mod 2. Note that the additive inverse of 0 is 0, since 0 plus 0 gives me 0 back again, so I get 0 back again. So that implies that minus 0 equals to 0, which we hopefully already knew. In Z mod 2, the additive inverse of 1 is 1, since 1 plus 1 equals to 0 mod 2. So that implies that minus 1 equals to 1 mod 2. So we can see that Z mod 2, it has both an additive identity of 0, and it does contain inverses for both the elements in the set. And it's closed, associative, and commutative, so it is an abelian group. We can also talk about groups under multiplication. So I can talk about groups under multiplication. Our additive identity in this case is denoted by 1, and our multiplicative inverses are denoted by x to the minus 1. Note 0 does not have a multiplicative inverse, so we need to remove 0 for the following sets to be groups under multiplication. Note that the multiplicative inverse of an integer is not an integer. Thus, the integers minus 0 is not a group under multiplication. For example, 2 is an integer, but its multiplicative inverse 1/2 is not an integer. This is the main difference when working over the integers. We do not have multiplicative inverses that are also integers. We can now define field. A field is a set that is an abelian group under addition. If we remove the element 0, it's also an abelian group under multiplication. And we also have the distributive property. So examples of fields include the real numbers, the rational numbers, as well as the integers mod 2. Again, the integers themselves, whole numbers, are not a field because we don't have multiplicative inverses, but all of these three sets are closed under multiplicative inverses, and they're closed under addition, multiplication. They have additive and multiplicative identities. They're associative, commutative, distributive, and so all of these things are fields. So back to our definition of free vector space. By the way, if you're familiar with vector spaces, every finite dimensional vector space is a free vector space. So a free vector space over the field F generated by the elements x1 through xk consists of all linear combinations of x1 through xk where our coefficients are elements in our field. And we do addition by combining like terms. Again, note that this is almost identical to the definition of free abelian group, except for now our coefficients need not be integers. Our coefficients will normally be elements in Z mod 2. We can write 4x1 plus 2x2, but that is the same thing as 0 mod 2. Since both 4 and 2 are even, they are both equivalent to 0 mod 2, and so we just get 0 mod 2. Thus, the vector space generated by x1 and x2 using Z mod 2 coefficients contains only 4 elements. Both our coefficients could be 0, in which case we get 0, or one of our coefficients could be 1 and the other one 0, in which case we either get x1 or we get x2, or both our coefficients could be 1, in which case we get x1 plus x2. So all linear combinations of x1 and x2, if our coefficients can only be 0 or 1, then we only have 4 different elements in our free vector space generated by x1 and x2 over our field Z mod 2. Addition is performed by combining like terms. So for example, if I have x1 plus x1, I get 2 of x1, but 2 is equivalent to 0, so I get 0 mod 2. Whenever we have 2 of something, we can cancel them out. Thus, in the next example, since I have 2 x1s, I can cancel them out, and I'm left with only 1 x2 mod 2. In the last example, nothing cancels out. We don't have any pairs of things, and so we just get x1 plus x2 mod 2. In the last lecture, we looked at an example of a graph with 4 vertices plus 5 edges. Now let's look at that example mod 2. Now mod 2, I have 0 vertices and 1 edge mod 2. Remember, when working mod 2, even numbers are represented by 0, so 4 equals to 0 mod 2. So mod 2, I have 0 vertices. And odd numbers are represented by 1 mod 2, so 5 equals to 1 mod 2. So mod 2, I just have 1 edge. Thus, 0v plus 1e, or just e, means I have an even number of vertices and an odd number of edges. If I didn't show you my graph, then 0 vertices plus 1 edge would only tell you that we have an even number of vertices and an odd number of edges. Thus, when we work mod 2, we lose a lot of information. But mod 2 arithmetic is computationally very fast, and thus one can analyze much larger data sets when working mod 2. We are still interested in labeling each vertex and labeling each edge. And while we can add objects of different dimension, most often we will be interested in sums of elements in the same dimension. We are still very interested in cycles, so I can talk about the cycle E1 plus E2 plus E3 and the cycle E3 plus E4 plus E5. Last time we cared that we traveled in 2 different directions when traveling along the edge E3 when describing these 2 cycles, so we looked at oriented graphs. But if I wish to reverse the orientation of an edge, I just multiply that edge by minus 1. So I go from E to minus 1 times E. But in Z mod 2, 1 equals to minus 1, and thus E equals to minus E. So if we have E equal to minus E, I no longer need an arrow to distinguish these 2 edges. So when we work with integer coefficients, I need oriented edges since E does not equal to minus E when working with oriented edges. But in Z mod 2, E equals to minus E, so I no longer need to orient my edges, and so I can have unoriented edges when my coefficients are in Z mod 2. Note that unoriented edges is unique to working with Z mod 2 coefficients. If 1 does not equal to minus 1, then E does not equal to minus E. So if our coefficients are integers or real numbers or anything where 1 does not equal to minus 1, then E won't equal to minus E, and so we will need oriented edges. But in the special case of Z mod 2, then we can work with unoriented objects. Let us now compare working with oriented versus unoriented objects. With oriented edges, the edge E3 canceled out algebraically when I added these 2 cycles together, E1 plus E2 plus E3 plus minus E3 plus E5 plus E4. With Z mod 2 coefficients, and unoriented edges, the edge E3 still cancels out because I get 2 copies of the edge E3, and 2 equals to 0 mod 3. So when I add together these 2 cycles, the edge E3 still cancels out, and I get the cycle E1 plus E2 plus E5 plus E4. When I take the path E1 plus E2 plus E3 plus E1 plus E2 plus E5 plus E4, note that I lose the information that I travel along the edges E1 and E2. Since I traveled along them twice, they cancel out since 2 equals to 0 mod 2. And I traveled along the edge E2 twice, so it cancels out, and so I only see E3 plus E4 plus E5. So again, working mod 2, we lose information, but it is worth the computational efficiency. Note that regardless of the path, if I have 2 of an object, I can cancel them out in pairs, leaving me with E3 plus E5 plus E4. With oriented edges, the boundary of E1 was V2 minus V1. We used the minus sign to denote that the edge E1 pointed from V1 to V2. With Z mod 2 coefficients, it's simpler. The boundary of an edge is just the sum of its 2 endpoints. So the boundary of E1 is just V1 plus V2. This makes sense since 1 equals to minus 1. I know that V2 minus V1 equals to V2 plus V1 mod 2, since minus 1 is equal to plus 1. The boundary of E2 is the sum of its boundary vertices, V3 plus V2, while the boundary of E3 is the sum of its boundary vertices, V1 plus V3. If we add together these boundaries, then all the vertices occur in pairs, thus everything cancels out, and we just get 0 mod 2. Remember, this is what we wanted. Since E1 plus E2 plus E3 is a cycle, it does not have any boundary, thus the algebra gives us what we expect. The boundary of a cycle is 0. Recall that we use this shorthand notation to denote the boundary of an object. So the boundary of a cycle is 0. If we now look at faces, if we have oriented faces, there are 2 possible orientations, clockwise and counterclockwise, or F and minus F. But with Z mod 2 coefficients, 1 equals to minus 1, so F equals to minus F. Thus, with Z mod 2 coefficients, we never need to worry about orientation. So all our complexes will be unoriented. So the building blocks for a simplicial complex using Z mod 2 coefficients will be unoriented. We can start off with 0-dimensional vertices, which we will call a zero simplex, where the boundary of a vertex is 0. We can also have 1-dimensional edges, also called one simplices, where the boundary of a 1-dimensional edge is the sum of its 0-dimensional boundary vertices, so we get V2 plus V1. We can also have 2-dimensional faces, also called a two-simplex, where the boundary of a two-dimensional face is the sum of its one-dimensional boundary edges, E1 plus E2 plus E3. We can also have solid three-dimensional tetrahedron, also called a three-simplex. The boundary of the solid three-dimensional tetrahedron is the sum of its four two-dimensional faces. So its boundary will be the sum of the face V1, V2, V3, plus the back face V1, V2, V4, plus the bottom face V1, V3, V4, plus the remaining face V2, V3, V4. We can also have n-dimensional simplices, and its boundary will be the sum of n-1 dimensional boundary simplices. But we will ignore the notation for now and focus on examples we can draw. There is an optional lecture on a terse introduction to simplicial complexes, giving more details using oriented simplices, but that lecture is optional.